This is section 3.9, and in this section, we will talk about the derivatives of logarithmic and exponential functions. Let's start from the general exponential function, and the only tool that we have to get the derivative, to find out how the derivative looks like, how the derivative behaves, we have the limit definition. Derivative of the function is defined as the limit as h goes to 0, f of x plus h minus f of x over h. Of course, we do remember this definition, limit definition, from the beginning of the chapter. Now I will evaluate this difference quotient for function a to the x. Then we can see we have a to the power of x plus h. That's the evaluation for f of x plus h. This is just f of x, which is a to the x, and divide by h. Okay, now we have to use a couple of rules and try to evaluate how this expression behaves if h is almost 0. This form, a to the power of x times a to the power of h, of course, is a to the power of x plus h. I factor out the common factor a to the x, and we have this. A to the x with respect to h, which we don't really see h in that expression, we can put outside because that's just the constant. Then we have to follow the steps and we have to focus on this limit. If we can get that limit, that's the success. That will be the formula. One thing, it's interesting because that boxed limit, if I add 0 to the h, I'm not changing anything, and a to the power of 0 is 1. I did change this limit a little bit, and from that form, we may notice that this is the derivative. I think I even said this. Derivative of the function a to the power of x at 0. Okay, we can see that limit is the derivative. But we still don't know because it's ironically the derivative of the function a to the x defined in terms of the derivative at 0. We're still missing that formula. But also what is interesting, derivative, that's what we're looking for, is going to be proportional to the function itself. Yeah? Derivative, which is the rate of change of the function, slope of the tangent, is proportional to the function itself, to the height. Slope will be proportional to the height, to the value of the function. It's really nice property of the exponential function. Okay, I do have all of this information. We can see slope is proportional to the height. The equation states that the rate of change of any exponential function is proportional to the function itself. Yeah, that's the nice property. Okay, I do have this, actually this. Okay, that value, derivative of the function a to the x at 0 is equal to natural log of a. And like in order to prove this, we simply have to compute this limit. Okay, because this is indeterminate form, because that limit, I can maybe remove this, that limit will give us this value for the function a to the x. And we will get natural log of a. We will focus on this type of limit later, but at the moment, I'm just providing the final answer. I do have a little bit of numerical proof, and that means let's see why derivative at 0, or maybe that limit, that will be easier. This limit is actually equal to natural log of the original base, a. of this exponential function. Okay, and we will look at this, and you probably also notice the formula. Now we have the formula. Derivative of exponential function a to the x is equal to a to the x times ln of a. Okay, I can even write this. I will have a nice summary, but derivative of a to the x is the same function, a to the x times natural log of a. Yeah? But let's just prove that ln of a little bit of numerical values. What I did, I have the table, and this is, of course, the limit. We recognize, we can see h is approaching 0, is getting smaller and smaller. And instead of general a, I just choose the base 2 and base 3, just to see how this behaves. And when we substitute instead of h, smaller and smaller value, 0.1, 0.01, 0.001, the numbers, the outputs, they behave like this. 0.7177, 0.696969, and then respectively for the base 3, 1.16, 1.104, 1.09, 1.098. And we may say that that's run like a numbers, but when we look closer, these numbers are actually natural log of 2, natural log of 3. They getting closer and closer to these values. Okay. Oh, and we can see, because we knew it that from the previous slide, that it has to be natural log of the base a. A is 2 and 3 respectively, but that's how this works. Okay, that means definitely depends on the base. That limit is approaching natural log of that value, which is in the base. Okay, that's the proof. Now, we also have a little bit of like a small question on the side, because I did pick the base 2 and I picked the base 3. And we know that this is ln of 2, this is ln of 3, is approaching. And numerical values are showing us that natural log of 2 is like less than 1. Natural log of 3 is more than 1. And what we want, we would like this limit to be 1. Yeah, like to be exactly 1. Now the question is, what base? Yeah, I have this question mark. What base we have to put for the limit to be equal to 1? Okay, of course, we know that this is ln of the base, ln of that question mark. I know that when you're probably watching this now, you will tell me right away, ln of e, natural log of e is 1. I think this is also one of the way to define the number e. That's what we wanted. We wanted that limit, because this limit is quite important to be exactly 1. Yeah? And if the base is e, this limit is 1. 1, of course. I mean, that's how it's one of the definition of the number e. Yeah? Of course, we also have another one. We will talk about this a little bit later. When x goes to the infinity, 1 plus 1 over x to the power of x, this is also e, but that's different way. But that's also the definition of the e. But this is the limit. Okay. And then I have these graphs. Now we can definitely see, because we will develop the formula for the derivative of the natural exponential function e to the x. But you can probably guess, since ln of e is 1, derivative of e to the x is just the function itself. That means derivative, slope, slope of the tangent line or slope of the curve to the function e to the x is just defined like this, the same like the function e to the x. And respectively, for the corresponding x value, we can calculate the numerical number. Slope at 0, e to the power of 0 is 1. Slope at 0 is 1. And then slope at any point, if we have the point, a little bit x, f of x, but f of x, of course, is e to the x. Slope at this point will be the derivative e to the x. Okay, and then derivative of the exponential function e to the x is e to the x times ln of e. We just following the general one, not squared, because we just learned derivative of a to the x was a to the x natural log of a. In our case, for the natural exponential function, we have e, and ln of e is 1. Then derivative of e to the x is just e to the x. We really like this formula. When we add the chain rule, e to the power of u, derivative of e to the power of u is e to the power of u, the same function always, and follow the chain rule times derivative of the inner function. Exponent is inner function. If u depends on x, it will be derivative of u with respect to x. Okay, what we have? Because in this section, we just need 4 new formulas. We have 2 for the exponential functions. I will even copy this one more time. E to the x is just e to the x without the chain rule. A to the x is a to the x ln of a. Okay, now I believe I do have the logarithmic function. Okay, logarithmic function, let's start with the natural one, ln of x. Of course, domain is just the positive numbers, positive real numbers. And we're looking for the derivative y prime or dy dx. Of course, we don't know the formula. But what we can do, we can take this function and we may change the form for the exponential one. E to the y equals to x. We remember the definition of the logarithm and or definition of the exponent. Okay, now looking at this equation, e to the y equals to x, we may realize that this is definition of the function y, a formula for the function y, but the implicit form. Let's use the implicit differentiation, take this equation like it is, and take the derivative of both sides, derivative with respect to x. Derivative of e to the y is e to the y times y prime, or dy dx. Derivative of x is 1. Perfect. Now I will divide both sides by e to the y because we're looking for dy dx. We're still looking for the derivative of the function y. Okay, and also we can see that this e to the y is x here, 1 over x. We did it. Derivative of the logarithmic, natural logarithmic function ln of x is just 1 over x. Of course, we will respect the domain for all x is greater than 0 because that's where the ln of x is defined. That's the first formula. We need one more. Okay, derivative of ln of x, 1 over x, and applying the chain rule, derivative of ln of u, assuming that u is the inner function which depends on x, it is 1 over u, 1 over that quantity times u prime, times derivative of u. Okay, and let's try. We're missing one formula, but we will get to this. Okay, derivative of natural log of sine of x. It's 1 over sine of x times derivative of sine of x. Done. Cosine over sine is cotangent. Derivative of natural log of x plus 1 over square root of x minus 2. This one, we may, of course, I can say that this is my u quantity, and I can say derivative is 1 over u times u prime. So I have to flip this fraction, then I have to use the quotient rule and differentiate. But also, in this case, what we can do, before starting like the derivative differentiation process, we may use the properties of the logarithm, and if the input is, we can see the quotient, this indicates the subtraction, the difference of two logarithms. Okay, always please remember, because then we can get complicated formula. Okay, this one is good because this one is ready to. This one I can still simplify. I can say 1/2 because square root is 1/2, and that 1/2 we can place in front. Okay, and now I believe we are ready to differentiate. Derivative, natural log of x plus 1 is just 1 over x plus 1 times 1, because derivative of x plus 1 is 1. Copy constant, derivative of ln of x minus 2 is 1 over x minus 2 times 1, because derivative of x minus 2 is 1. And I think we can leave it like this. Yeah, we can see it's just one step if we simplify before the derivatives. Oh, now we have ln of absolute value of x. We have to differentiate this. This indicates that domain could be any real number. Any real number is good. X belongs to R, all of the real numbers. What we will do, always to perform some exercise, calculus exercise with the expression with absolute value, we have to rewrite without the absolute value. I mean, if x is positive, yeah, this will be just here, we can ignore absolute value. However, if x is negative, I cannot leave it like this because that's negative. I will put extra negative. That extra negative, ironically, is making expression positive. Okay, and now let's differentiate. Derivative of ln of x is 1 over x for all of the positive x's. And now ln of negative x, 1 over negative x times negative 1. Follow the chain rule. And negative will give us the same answer, 1 over x positive, for all of the negative x's. So we can basically see that derivative is actually the same. And that's okay, because this is no more logarithmic function. If function is positive, we can see logarithmic function looks like this, ln of x. But ln of negative x looks like this. This is 1, I mean negative 1. Okay, oh, no, negative will be the other way. Argument is negative, the input. Okay, this way, then we have reflection about the y-axis. Okay, that's the graph of our function. And basically, if the x's are positive, this will be positive. And makes sense, because we remember slope of the tangent, slope of the tangent, slope of the tangent. That's the derivative is positive. But if x's are negative, 1 over negative number, it will be negative. Negative slope, negative slope, negative slope. Everything works. That's basically the derivative, I can write again, of this function is 1 over x. But respectively to the part of the number line, positive or negative value will take place. Okay? Another formula, which actually is the last one, general logarithmic function, log base a. any value of a. Of course, a is positive and never 1, but any number of a with that interval. And let's see what we can do. We have to find the derivative. We don't know, yes, how the different base affects the derivative. Before, I can actually use the pre-calculus formula, how to change, we can change the base. Changing the base formula looks like this. Log base a of x is equivalent to log of any base that we like. B, we can put 3, 4, 5, 6, 7, 1.5, I don't know, any number, less than 1, greater than 1. Of course, not negative and not 1. A and B are always positive and they are never 1, but this is part of the definition. Okay. And we can see back, and then that x, that input stays, and that base become an input. But this is just the formula. And now what we can see, instead of, I can use actually this one. That's also, I choose the base e. If I choose the base e, a logarithmic function with the base e is simply ln. ln of x, ln of a. Now, ln of a in the denominator is constant. I can put outside the formula, right? 1 over ln of a, 1 over ln of a. And we may notice we only end up with our known formula. We have to differentiate ln of x. Derivative of ln of x is, of course, this. And that's the derivative of, oh, I have the chain rule, okay, but the first box is just the derivative of a general logarithmic function. Log base a of x is 1 over x, but in the denominator we have to multiply by ln of a. Yeah, a little bit similar, like concept, idea, like the general exponential function. And now, following the chain rule, log base a of u, it's 1 over u, ln of a, that's the main formula, and follow the chain rule times u prime. Or we can say du dx. Okay, let's differentiate. Log of 2 plus sine of x. If the base is not written, we know that the base is 10. Okay. Derivative of the logarithmic function is 1 over that quantity times ln of 10, because that's different, and times derivative of 2 plus sine of x, derivative. Okay, I can put ln of 10 in front, 2 plus sine of x. Derivative of 2 is 0. Derivative of sine of x is cosine of x. This is the final answer. Let's differentiate the next one. 2x log square root of x. We can definitely see x and x products. Yeah, please be careful with applying the product rule. Please do not forget. Oh, no, let me simplify something before. Okay, we have 2x times. I see log of square root of x. Square root of x is, of course, x to the power of 1/2. We can place that 1/2 in front, that's not ln, in front of the logarithmic function. And not even mentioning, I can simplify this, 1/2 times 2. We have x log x times, of course. I'm just stressing out that dot because we can't afford to miss product rule. Okay, but please notice, like with this, again, the simplification. Okay, derivative, product rule. Derivative of x is 1 times log plus x, and derivative of logarithmic function. Log of x, 1 over x times ln of 10. Because we know that's the base. If the base is not written, it's always 10. Okay, we can simplify a little bit. The final answer is log of x plus 1 over ln of 10. Of course, these two x's are gone, x and x. Okay, good job. I will suggest to even cover the solution and just solve it again. Yeah? Or doing the homework assignments, you will also practice. Okay, log base 5 x times e to the x. Yeah, this one we may also simplify. Let's maybe do it. Or we may use the product. Actually, let's try. Let's do not simplify first, okay? And then we will try to rewrite a function and do it again. Okay, log base 5 of x e to the x. Derivative is 1 over that quantity times natural log of 5, because we have the base, and times derivative of that input. Okay, x e to the x ln of 5. And we have to remember we have product x e to the x. Derivative of x is 1 times e to the x plus x, and derivative of e to the x is just e to the x. Okay, we have e to the x plus x e to the x e to the x natural log of 5 times, actually times. We can factor out 1 plus x, oh, that's x, and then x e to the x natural log of 5. Since every number is involved in the product, the final answer, oh, can I squeeze it, is 1 plus x over x ln of 5. Okay, not bad, not bad. However, we may try to split. Maybe we don't have to, but let's, in this case, of course, we have log base 5 of x, and since we're multiplying x and e to the x, this indicates the addition. When we're adding the same logarithm with the same base, we can simply split as addition. And one more thing, this one is ready to be differentiated, but that x we can place in front. And unfortunately, if this will be ln of e, it will be 1. We have to keep it. It's just constant. Okay, let's try. Derivative of log base 5 of x is 1 over x ln of 5 plus x times the constant, like 2x, 5x, 6x, is just 2, 5, 6. It's just log base 5 of e. And you may try, but this is the same. That's actually the same answer. You may try to use some logarithmic properties, exponential properties, and try to get the answer. But if we will change the base, because we have to change base, right, I will just change for ln of e, ln of 5, as we remember. And then actually, I make small mistake. This is supposed to be 5. Okay, and this is ln of 5, and this is 1 over ln of 5. When you get the common denominator, I believe you will get this. You can try. Okay, but we can see, we can simplify in this case, or we may not simplify. Okay, what else? Oh, I also have, because we didn't practice, I just have, I will just repeat, even if we started nicely our session with the definition of the derivative, we know the formula for the derivative. Yeah, I can ask you, maybe you can, if you're watching this session, you can say derivative of a to the x is a to the x times ln of a. Let's see what I did. I did use, because I have different way, which I can also show you. But in order to get the derivative one more time without using the definition. However, we will need to know what is derivative of e to the x, and we will need to know chain rule. Okay, I rewrite expression a to the x as a e to the ln of a to the x. Because we know function e and ln is inverse to each other, they cancel. This expression cancel, only a to the x stays. Then both of the lines are equivalent. And now that x, we know that exponent can be placed in front of ln, x times ln of a. Now I will take this equation like it is. Okay, it's not necessarily implicit because y is isolated on one side, but I will differentiate y and I will differentiate the right-hand side. Derivative of y, of course, is y prime or dy dx, depends how we like, what notation we prefer. And now, derivative of e to the x ln of a. It's the same function, e to the x ln of a, times derivative of the exponent, which is just ln of a. Okay, and now we can put that x, of course, we can put this x actually, ln of a to the power of x. Right, we know and ln of ln and e can cancel out, only a to the x stays. And of course, we knew this formula, but it's also nice practice to look at this formula from different angle. A to the x times ln of a. And the chain rule, e to the u, a to the u is a to the u, ln of a times derivative of u prime. Okay, let's differentiate 2 to the power of cosine of x square root of x. It's exponential function, then I will copy the same function times ln of base, ln of 2, and times derivative of the exponent. Derivative of cosine is sine of x, derivative of square root of x is 1 over 2 square root of x. And we can leave it because we nicely see each component of this formula. 2 to the power of x squared minus 1. It's exponential function, derivative is just the same function, times ln of the base, 2, times derivative of x squared minus 1, 2x. We can also leave it. We can simplify a bit, but we can leave it. And, oh, okay, let's try. Excuse me. We have 2 to the power of this number. It's exponential function because x is placed in the exponent. The variable is placed in the exponent. Derivative is the same function times ln of base and times the derivative of the exponent, which I will rewrite like this because it's not, we need a couple of extra steps, ln of 2. Okay, derivative of 3 to the x squared is, that's exponential function. The same function, ln of 3 times derivative of the exponent, which is 2x. This one is easy, okay? Now again, we do have each part, each component of this expression. And the chain rule was actually twice. We had 2 inner functions. Okay, e to the tangent of x. That's natural exponential. It's exponential function, derivative is the same function. And you can see I don't need to write ln of e. Yeah, just the same function times the ln of e, but ln of the base now. But times derivative of tangent. Derivative of tangent is secant square of x. That's it. Okay. That's all of the formulas that we have to take away from today's session. Okay, natural exponential and logarithmic, general exponential and logarithmic. Okay, please make sure that you remember But even if you don't have to actually sit and memorize this, you can just simply practice. We will do one more thing. Because what's happened, we may have, like what we just learned. We just learned exponential, because I don't have logarithmic here. We just learned number 3, a to the power of g of x, or a to the power of u. Derivative is a to the power of g times ln of a, and follow the chain rule times g prime. If we have power function like x squared, x cubed, we will know what to do. 3, let's say x cubed, we will put 3x squared. Or if this is more than x, we will follow the chain. It means number 2 is a power function. Okay, number 2 is a power function. This is exponential. Okay, that's power function number 2. Number 1, even if we have even if this looks like a power or exponential, but both of them are constant, like for instance 2 to the power of 3, that's constant. Derivative of constant is 0. Yeah, we can deal with this. Sometimes number 2 and number 3 are a little bit like mixed together, but please always note, if x is placed in the exponent, we follow the exponential formulas. If x is placed in the base, we follow the power rule. But what we may also see, we may see a little bit different creature, function taken to the power of another function. Like for instance, x to the power of x, or maybe x to the power of sine of x, or maybe cosine of x to the power of 2 to the x. Oh, crazy. Of course, that's crazy functions. But what is important to remember, they are not exponential and they are not power. Because we see x in the exponent and in the base. That means it's kind of like a mixture. And at first, we don't know how the function looks like. And of course, we're not applying formula 2 or formula 3. No, we will use something that is called logarithmic differentiation. And just in case, let's see what we will do. We have some steps. Okay, we will take the logarithm of both sides, use a couple of properties of logarithm, use the implicit differentiation, and solve for y prime. And for instance, x to the x. And we can see, looks like this. We will actually change this for the logarithmic form. Or exponential, but this is the function. It's quite crazy function. But again, having x and x in the base, in the exponent, it's a little bit crazy. That's what we will do. We will take natural log of both sides. Okay, we're still looking for y prime. We have to remember, we're still looking for the derivative. Okay, I can copy this one more time, and I can place that x in front. Okay, now we have just the product. Let's differentiate. I will differentiate with respect to x both sides of the equation. Right? Natural log of y, which y is still a function which depends on x, and x ln of x. Derivative of ln of y is 1 over y times y prime. Derivative of x ln of x, we will use the product rule. Derivative of x is 1, ln of x, plus x, derivative of ln of x is 1 over x. Okay, y prime over y, natural log of x plus 1, because we can cancel out these two. And now we're looking for y prime. Let's multiply both sides by y. And this is almost the final answer. The only thing is we will not keep the answer in terms of y. We will keep the answer in terms of x only. Y was defined as a x to the x. This is the final answer. Okay? So please remember, take the natural log of both sides. Just in case if we end up having this form. Let's integrate, differentiate one more, tangent to the x. tangent x to the x, and yeah, and we will be done with these derivatives. Okay, natural log of y, natural log of tan x to the x. Natural log of y, we don't really need the parentheses. That x, if we have logarithm, we can place in front. Okay, let's differentiate with respect to x, implicit differentiation, both sides. X ln of tan x. Okay, derivative of ln of y is 1 over y, follow the chain rule, times y prime. Derivative of x is 1 times ln of tangent, product rule, x times derivative of ln of tangent, 1 over tangent x times derivative of tangent secant square. Okay, natural log of tan x plus, we can put x secant square of x over tangent of x, because we cannot really simplify. And we will multiply both sides by y, natural log tan x plus x secant square of x over tan x. And of course, instead of y, we will put tan x to the x. I will remove both of them and I will just put the original formula in terms of x, because this is y. Yeah. Okay. We learn 4 formulas plus the implicit differentiation. Please practice even solving the same problems, not even mentioning about the homework assignments. You can definitely master these concepts. Thank you.